Today we are going to discuss magnetic dipole. What is a magnetic dipole? What is magnetic dipole moment? And then we'll try to find out expression for magnetic field intensity on the axial and equatorial line of a magnetic dipole. We'll also do what is the expression for the force and the torque on a magnetic dipole, which is kept in a uniform magnetic field. Then we'll try to find out what is the work done in rotating a magnetic dipole in uniform magnetic field, and what is the expression for potential energy stored in a magnetic dipole. We'll also see what is the most stable and most unstable orientation for a magnetic dipole in uniform magnetic field. So let's start with magnetic dipole. Suppose we take a bar magnet. We can take bar magnet and we can treat it like a magnetic dipole, because for the magnet, as we know that monopoles do not exist. Whenever magnetic poles will occur, they will always occur in pairs. So in a bar magnet, if you see, the magnetic strength is maximum near its ends, and those points where it has maximum value, we call them as the poles of the magnet. So suppose this is your south pole and this is the north pole. We can assume as if there are the magnetic charge similar to your electric dipole. Like in electric dipole, if you consider, you have the negative and the positive charges separated by a small distance. Earlier for the magnet also, it was believed that magnetic property in the magnet is due to magnetic charges. So they call them as the magnetic charge, and they also assume initially that they are of two types. So they call it as the negative magnetic charge and positive magnetic charge, and they believe that it is concentrated more near the poles, those magnetic charges. Earlier they used to represent as minus qm and plus qm, just similar to the charges which we are taking. But nowadays it is taken as the pole strength. Pole strength to represent the factor which is responsible for the magnetic property of the magnet. So here, if it is the south pole, we assume that we have the pole strength minus m, and it is the north pole, so it is plus m. So these will be the pole strength which is responsible for the magnetic property of the magnet there. And now as we are saying that the poles of the magnet, they are not exactly at the ends. So here, if you consider this length, that is the distance between one end to other end of a magnet, that we call it as the geometric length. Whereas the distance between the actual position of the poles of the magnet, they are taken as magnetic length. And we can see that magnetic length is less than geometric length. In fact, we have a relation between magnetic length and geometric length given as magnetic length is 0.84 times geometric length. So this is the relation between magnetic length and geometric length. If it is 100 centimeter, this distance will be 84 centimeter. So here, as we have the now negative and the positive pole, magnetic poles, which is the south pole and north pole we are taking. So in this case, we can treat it like a magnetic dipole, because here also you have the two equal and opposite poles separated by a small distance. So this is your minus m plus m, and this length or the distance between the poles, we take it as 2L, just similar to electric dipole. And now if this is the center of the dipole, so here magnetic dipole moment, this will be pole strength multiplied by length or distance between poles. So this will be equals to m into 2L, and we represent the magnetic dipole moment by capital M. So this magnetic dipole moment in vector form, we can write it as 2L. This will be in a direction from south pole to north pole there. So this is the direction of the magnetic dipole moment. Now, based on the relation between the dipole moment and the pole strength, we also have some conceptual type questions. Suppose the question is given that we have a paramagnet or magnetic dipole. It is cut into two equal halves. One say along xy, or second case it is cut along x dash y dash, and it is cut into two identical halves. What will happen to the pole strength and dipole moment in the two cases? So here, first if you take, when cut along xy, new pole strength, because we can assume as if the magnetic charges are concentrated near the poles. So if you are cutting into two equal halves, they will also get divided into two parts. So this m dash will become half of m. That is the original pole strength. And the dipole moment, which is your 2 times m dash l dash. So this one will be equals to m by 2, because there is no change in the length. So it will remain 2L. So this will give you 2ml by 2, or that is your m by 2. That means if it is cut along xy, in that case the pole strength will become half and magnetic dipole moment will become half. Magnetic dipole moment will become half just because the pole strength has become half. But when we cut it along x dash y dash, so when cut along x dash y dash, in that case m dash. Now if you are cutting along x dash y dash, the pole strength of the magnet, it is not getting disturbed, because accumulation of the magnetic charges near the poles, that remains same. Of course, here opposite poles will be developed or it will be induced. So here m dash will remain same as m. That is the pole strength. But if you consider the magnetic dipole moment, this will be now, pole strength has remained same, so it is m. But now the length will become half. So as the length becomes half, it is your 2L by 2. So this is again 2ml by 2 or m by 2. So this time pole strength will remain same, but dipole moment will become half. And this time dipole moment is becoming half just because the length has become half. In the earlier case it has become half because the pole strength has become half. Suppose we want to find magnetic field intensity due to a magnetic dipole on its axial line. If you have a magnetic dipole, then line joining the negative and the positive poles, that is the south and the north pole, that will be the axial line. A line perpendicular to the axial line and passing through its center, that will be the equatorial line. So here we want to find magnetic field intensity on its axial line. So suppose Sn is the magnetic dipole having pole strength minus m and plus m, length 2L, dipole moment capital M, and we want its magnetic field at a distance r from it at a point P. Suppose B1 is the magnetic field due to north pole or due to the pole strength plus m, and B2 is magnetic field due to south pole there, and B we are taking as the magnetic field due to this entire magnetic dipole. So B1, this is magnetic field due to m. So this is your mu naught by 4 pi m by r minus L whole square, and this will act along OP. This will be acting in this direction. Similarly, B2, this is magnetic field due to minus m. So this will be mu naught by 4 pi m by r plus L whole square, and to represent its direction we are writing that it is along PO, or if you want to write it along OP, then it will be with negative sign. So in that case it can be written as your minus mu naught by 4 pi m by r plus L whole square, and this is along OP. The net magnetic field, that will be B1 plus B2, which is mu naught by 4 pi m by r minus L whole square for this term, that is B1, and for B2 it is minus mu naught by 4 pi m by r minus r plus L whole square along OP. So which is equal to mu naught by 4 pi m. Now we can take LCM, and for that, if you simplify, it will be your r plus L whole square minus r minus L whole square in the numerator, and denominator it will be your r square minus L square whole square, because these two terms r minus L and r plus L, this is like a plus b into a minus b. So it was your r square minus L square, and since the power was 2, so it is square of that term. So now here, if you just expand this, you will have r square plus L square plus 2rl minus r square minus L square plus 2rl. Now this term, r square, L square, they will get cancelled. So now what you will have? You will have 4rl by r square term whole square, r square minus L square. If I am taking outside, then we can write it as r power 4. So it is your 1 minus L square by r square whole square. R term we can cancel, and now this 4ml we can write it as 2 times 2ml. So that for this 2ml I can write m, that is the magnetic dipole moment. So this B will be your mu naught by 4 pi 2m by r cube 1 minus L square by r square, and direction will be along OP. So this is this expression for magnetic field, and if you write in vector form, in that case you can write it as B vector equals to mu naught by 4 pi 2m vector by r square r cube 1 minus L square by r square whole square. So that will give you the magnetic field due to magnetic dipole on its axial line. For very short dipole, that means a magnetic dipole whose length is very small as compared to the distance where we want to find magnetic field intensity, we can take L very small as compared to R. So in this expression, if you substitute that L is very small as compared to R, L square by R square term will be negligibly small as compared to 1. So if you neglect that one, you will get B equals to mu naught by 4 pi 2m vector by R cube. Remember, this is similar expression for electric dipole case where we want to find electric field intensity on the axial line. There you have the electric field intensity here, and it was 1 by 4 pi epsilon naught as a constant there, and it was 2p vector by r cube. There it was the electric dipole moment. Here we have the magnetic dipole moment. Derivation is almost similar to that of the electric dipole. Just terms you have to put accordingly. Like if it was electric field intensity in case of electric dipole, here it is the magnetic field intensity in case of magnetic dipole. There it was the charges, here we are taking as the pole strength there. So in the same way we can derive the expression. Let's now try to find out expression for magnetic field intensity due to magnetic dipole on its equatorial line. So suppose this is the magnetic dipole Sn, we have pole strength minus m plus m, and it's of length 2l, we want to find magnetic field intensity on the equatorial line at a distance r from it. B1 and B2, once again we have taken as the magnetic field due to the pole strength plus m and minus m at the point P. Their direction will be, B1 will be in this direction along NP, and B2 will be in the direction PS. Now B1 and B2 in magnitude, they will be equal, and its value will be mu naught by 4 pi m by r square plus l square. Now if I resolve this B1 and B2, I will get the component as B1 sine theta here and B1 cos theta along the perpendicular direction of equatorial line. Similarly for B2 also will get B2 cos theta 2 in perpendicular direction to equatorial line, and along equatorial line it is your B1 sine or B2 sine theta. As B1 and B2 are equal in magnitude and B1 sine theta, B2 sine theta, they are in opposite direction, so they will cancel out one another. Whereas in the perpendicular direction to equatorial line, the components like B1 cos theta and B2 cos theta, they will add up together. So the net magnetic field will be only due to B1 cos theta and B2 cos theta there. So the net magnetic field B, if you consider, B will be equals to B1 cos theta plus B2 cos theta, which is 2 times B1 cos theta, because B1 and B2 magnitude wise the two are same. So if you put that, it is mu naught by 4 pi m by r square plus l square, and for cos theta I can write this L by r square root over r square plus l square. So this is your L by root over r square plus l square for cos theta term. So this is your mu naught by 4 pi 2ml divided by r square plus l square power 3 by 2. And this is your mu naught by 4 pi m by r square plus l square power 3 by 2, and this is along px. So this is along px. So this is your B vector. This is along px. Now we can also write this as B equals to minus 4 mu naught by 4 pi m vector r square plus l square power 3 by 2. Why? Because m vector, that is magnetic dipole moment, will be in the direction south to north. So it is from left to right, whereas this direction is from right to left. So it is in opposite direction to the magnetic dipole moment. So we have substituted with negative sign. So this is the expression for magnetic field intensity due to magnetic dipole on its equatorial line. And suppose now we want to find out magnetic field intensity due to a very short dipole. So here we'll put for L very small as compared to R. So for very short dipole, L is very small as compared to R. So B vector will be equals to minus mu naught by 4 pi m vector by R cube. So this is the expression for magnetic field intensity on the equatorial line for a very short dipole. Let's now take force and torque on a magnetic dipole in uniform magnetic field. So suppose there is a uniform magnetic field B acting in a region where we have a magnetic dipole Sn having pole strength minus m plus m kept at an angle theta. So suppose we assume that this is kept at an angle theta with the direction of magnetic field. So if you consider the force on the pole strength plus m that will be equals to force on pole strength M, that is equals to MB, and force on minus M, that is negative pole or south pole there, that will be equals to minus MB vector. So the net force, that will be equals to MB vector minus MB. This is 0. So the net force on a magnetic dipole in uniform magnetic field is 0. And if the net force is 0, definitely in that case, there, as we have now two forces of same strength, MB acting there, but they are acting in opposite direction, so it can produce a turning effect there, or it can produce a torque in the magnetic field. So the torque experienced, this will be equals to force into perpendicular distance. It is a couple being produced there because you have the two equal and opposite forces there acting at the two ends, so it can produce a turning effect there. So this torque, this is equals to the force MB. And now if you consider the perpendicular distance, this is your perpendicular distance between these forces. And if this length we have taken, that is the length of the dipole is 2L. So obviously this length will be how much? 2L sine theta. So if this is the 2L sine theta, so we can write this perpendicular distance. So the perpendicular distance can be written as your 2L sine theta. So this is your 2mL B sine theta. This is the torque, or the torque can be written as capital MB sine theta. If you want to express that in vector form, also this torque can be written as your M cross P. So this is the torque in vector form. Now here you can see, if theta is 90, in that case pi by 2, then the torque will be equals to MB sine pi by 2, and that is MB. This is the maximum value. Whereas if you consider that if theta is 0, then the torque will be equals to MB sine 0, and that is 0. Whether it is a 0 or pi also, if you take that, there also it will be 0. So the torque on the magnetic dipole will be maximum when it is held perpendicular to the magnetic field, and it will have the minimum value when it is kept along the direction of the magnetic field. Suppose you want to find out work done in rotating a magnetic dipole in uniform magnetic field. There is no net force on the magnetic dipole, so obviously no translational work will be done. But as the torque is acting, definitely it can rotate the magnetic dipole in the magnetic field, and in that case, when it is turning, it will produce work done. So we can find out expression for the work done in rotating the magnetic dipole in uniform magnetic field. Let B be the magnetic field intensity of the field in which a dipole is kept, and suppose when it is kept at an angle theta, torque tau, when the magnetic dipole is at an angle theta with the direction of magnetic field, that is your MB sine theta. Suppose the dipole gets turned through d theta. So there is small work done. In turning through d theta. A small work done will be tau d theta. So that we can write it as your mb sine theta d theta. Suppose we want to find the total work done in rotating it from theta 1 to theta 2. So in that case, W will be integral of this dW. That is your mb sine theta d theta integral from theta 1 to theta 2. So this is equals to mb sine theta d theta integral will be your minus cos theta. So this will be equals to mb cos theta 2 minus cos theta 1, and that is equals to mb cos theta 1 minus cos theta 2. This is the work done. So this is the expression for work done in rotating a magnetic dipole in uniform magnetic field from theta 1 to theta 2. Let's take energy is stored in uniform magnetic field. As we know that work done on a system is stored as its potential energy. So work done, as we have taken, this is mb cos theta 1 minus cos theta 2. So the energy stored will also be equal to this expression, because whatever work is being done on the system, it is stored as its potential energy. So the energy stored will be mb cos theta 1 minus cos theta 2. Here, if we consider, if theta 1 is pi by 2 and theta 2 is theta, then the energy is stored or potential energy, this will be equals to mb cos pi by 2 minus cos theta, and this is your mb 0 minus cos theta, or that is equals to minus mb cos theta. So this is the expression for potential energy stored in the magnetic dipole in uniform magnetic field. In vector form, we can write u as minus m dot b. Now here we can get different cases there. Suppose if theta is 0, if theta is 180, if theta is 90. So if we consider if theta is 0, so u will be equals to minus mb cos 0, that is minus mb, which is the minimum value of the energy. Hence, it corresponds to most stable configuration. So this will correspond to most stable configuration of the magnetic dipole. If we consider theta is pi, then u will be equals to minus mb cos pi, and that is your plus mb, because the cos 180 is minus 1, so it will become plus here. This is the maximum value, and hence it corresponds to most unstable configuration. So that is the most unstable configuration for the magnetic dipole. And third case, if you consider, if theta is pi by 2, then potential energy will be your minus mb cos pi by 2, and that is 0. So here what you should remember that if theta is 0, that means magnetic dipole is kept in the direction of the magnetic field. Magnetic dipole moment and magnetic field intensity both are in the same direction. In that particular orientation, the magnetic dipole has minimum energy possessed. And if it has the minimum energy, definitely it will correspond to most stable configuration. However, if theta is 180, in that case, it will give the maximum value there. So it will have the value MB, and in that case, it will correspond to most unstable configuration. Many times you may be asked to identify the orientation which gives the most stable configuration, which gives the most unstable configuration. So if you know, if theta is 0, it corresponds to most stable configuration. If theta is 180, then it is most unstable. So you can easily write the answer. Some question may be there where they will say, what is the work done in rotating a magnetic dipole in uniform magnetic field from most stable to most unstable configuration? We know the formula for the work done, and most stable configuration is when theta is 0, and most unstable will be when theta is 180. So we'll put in this formula for work done, and we can find out what is the work done in rotating the magnetic dipole from most stable to most unstable configuration. So this is all about the magnetic dipole, and its different cases there. But you just remember one thing: if you have done electric dipole properly, and you know the derivation for the electric field intensity on axial line, equatorial line, force and torque on the electric dipole in uniform electric field, work done in rotating the dipole in electric field, energy stored, same type of derivation is there for magnetic dipole. You just have to use the corresponding terms there, and if you use that, you don't have to remember the two derivations separately. You remember one, you can easily write the other one.